Okay, hello. In this part of the video, I'll run you through a few examples. I hope you have watched Miss Ellie talk to you about same problem. Talk to you about gravitational field strengths and also the main ideas behind it. So today we're going to look at some past year questions. And if you're wondering, this is from page 17. Okay. At first, they will ask you to define gravitational field strength. Nice warm-up question. It will be gravitational force per unit mass. Okay, and the mass of a spherical comet of radius 3.6 km is approximately 1.0 times 10 to the power 13 kg. Okay, assuming the comet has constant density, find the gravitational field strength at the surface. So if it's at the surface, you can just conveniently substitute the radius, and that's all. It's a bonus question, provided you know the equation lah. Alright, so gm over r square, because per unit mass, one of the mass will disappear. So now you have a probe, 960 Newton on Earth, and now using your answer above, find the weight of the probe on the surface of the comet. So if you remember, right, on Earth, or in all cases, gravitational force or weight is known as mass times gravitational field strength. So on Earth, 960 Newton will be m times 9.81. So the mass of this probe will be 960 over 9.81. No? So on the comet, W is once again equal to mg. So if W is equal to mg, right, then you can just substitute the m 960 over 9.81 times g. That's all. Looks pretty light because it's a small comet. Now you have this second very weird shaped comet that is not a sphere. So obvious, right? It is not round. So now this second comet, the length is 4.5, the width is 2.6. Oh well, no, doesn't matter. So you are asked to suggest a similarity and a difference between the first spherical comet and this second weird shaped comet. So the first thing you can talk about when it comes to gravitational field is that it is always attractive. Gravity is always attractive. So that could be one. Okay, and if you want to write the second similarities, will be it will have the same order of magnitude. Now what I mean by same order of magnitude, if you look at the width, the dimension, they're around the same family lah, a few kms. So the gravitational field strength should be about the same because comets are made out of the same stuff. Alright, so differences. Well, comet in B will have a radial gravitational field line. I will draw the lines later for you. And comet in C has non-radial gravitational field lines. And because comet in B is radial, right, we can say that it is the same, the gravitational field strength is the same over the surface, and for the other one, it changes across the surface. Whenever you write comparison, you have to mention both, okay, especially if they are different. So I'm trying to draw the gravitational field line. It has to be perpendicular to the surface. So, I mean, 90 degree, 90 degree, 90 degree. You can tell, right, all these lines, there are certain places where the lines are close together on the surface. That means that, so like for example here, line close to the surface, strong field. Here we have weak field. And here you can see I'm trying to draw a radial field for you. You can also find this in your lecture notes. So this kind of radial field, right, you can see that it's fairly uniform. The line separation along the surface will be about the same. Okay, and in fact, if you zoom all the way in, you will get parallel lines. I mean, you can try zooming in, or if you want to, you can try drawing a circle, and then you go zoom all the way in. It will look like it's flat. But the Earth is not flat. You are a student of science, guys. Earth is not flat. Great. So radial lines, non-radial lines, and then one is uniform, one is non-uniform. Okay, always base your discussion off the shape or the pattern that you see. Alright, so here is weak. Here is weaker because the lines are further. Whereas these places here I will expect to be stronger. Alright, next question. So this one is from page 19. Okay, and since they ask you to define gravitational field strength, I copy paste. There are not many good things about doing this thing on OneNote, but this is one of them. I can just copy paste the same thing. Define gravitational field strength. So it's gravitational force per unit mass. So explain why, for changes in vertical position for a point mass near the Earth's surface, the gravitational field strength may be considered to be constant. So let's call the vertical position h. And Miss Ellie also mentioned to you about this in your lecture video. So changes in height is much less than the radius of the Earth. Like the radius of the Earth is 6.4 times 10 to the power of 6 meter. How many thousand meters are you going to change? It's not going to make a difference, right? So since gravitational field lines are radial, like the example just now, close to the surface, the field lines are almost parallel. When you zoom in, the curvature will flatten and the normal will look like it's parallel. But if you want to use equation, this time they allow, but there was another year where they don't really credit marks for equation, or you won't get full mark lah. So this is the equation now, because G is GM over RH. Pause the video for a bit. So because R is much bigger than H, so you can assume that the H is not there. Alright, next part. This is a pretty familiar question. The orbit of the Earth about the Sun is approximately circular, with a radius of 1.5. You are given the period, so determine the value m of the Sun. This is a perfect question. When it come out, everyone happy. You know why this 5 marks? 5 out of 100 marks, guys. Bonus, provided you remember to convert what you're supposed to convert lah. Okay, so but first explain your working. So gravitational attraction force provides the necessary centripetal force for the Earth to rotate around the Sun. Okay, so Fg is equal to Fc. We have done this in the previous video, so I am not going to talk so much. I will just substitute Gm m over r square. Okay, mass of the Sun, mass of the Earth. So the Earth is the one rotating, so in the centripetal force equation, me will be used. Alright, okay, so now substitute law, r cubed 2 pi over t. Now so I have a habit of rearranging the values so that all the substitution is already on one side. Then I can press calculator one go. Because when you don't do that, right, then you shift here, shift there, you might shift wrongly. In fact, sometimes if I do this also, I could also shift wrongly. So not sure one. Okay, let's hope I got square. Okay, no, I did not square. So, but my answer is correct, because I calculated sideways. So there's a square missing here. No, I'm not going to post edit anymore. It's 12. I want to go home. Alright? So, 2 here. Anyway, if you're wondering where the marks are, 1 mark is for you when you write the explanation. Okay? Does it have to be in sentence? Depends on the examiner law. Alright? The other mark is when you use the correct Fg and Fc equation. The other mark is when you equate omega as 2 pi over t square, and then the correct substitution, and then the final answer. 1, 2, 3, 4, 5. There's a square here. I didn't inherit, but I pressed correctly because the answer is correct. Alright, that's all. Let's continue. Okay. Moving on, we will look at the next question. Okay, and this next question will be about this ON10 paper 41. So again, define gravitational field strength. I also copy paste from the one on top lah. Okay, so I think this is page 31. Page 31 in your notes. Okay, if it's not, you can find lah. Anyway, you are asked to sketch the variation of gravitational field strength against distance. This is also in your lecture notes. Okay, so I'm going to sketch this together with you, but we are going to draw from the surface of the star to a distance of 4r from the star. And you know from this equation, right, that G is inversely proportional to r squared. So when it's inversely proportional to r squared, what does it mean leh? When you double the radius, you will 1 over 2 square, or GS over 4, the field strength. Okay, so this will be 3 square and this will be 4 square. So plot lor. Now this is a very old question, 2010. So the graph grid at that point given were a bit crude. But recent years, especially if you are doing my task, the recent years you will notice that they will actually give you a proper graph and they expect you to graph it at the correct coordinates. So please ladies and gentlemen, boys and girls, plot the graph properly, okay? And then so 0.25, 0.11, 0, this is 0.0625, 63. So half of half lah. So with a smooth, steady hand on the tablet. Very hard, you know, to draw on a computer. Join the point in a smooth curve. You got this. Oh, looks promising. Yay. Okay, something like this lah. So this one is 2 marks. 1 mark is for the general shape. So if you don't have time, you simply anyhow draw a decreasing gradient shape. You get 1 mark already. And then the other mark is for the values or the coordinate. Next question. The Earth and the Moon is considered to be spheres. You're given its mass. Okay, the radius of the Earth is RE. They are 60 times the radius of the Earth apart. Explain why there's a point between the Earth and the Moon where the field strength is 0. Well guys, I don't know whether you remember from the lecture, force is a vector. So force per unit mass is also a vector. So if also a vector, right, then if there's a point in between where the GE, because GE is attractive, so it will point towards the direction of the Earth. And GM is also attractive, will point direction to the Moon. So there will be a point where they cancel out. Okay, so first thing you need to mention, gravitational field strength is a vector. Okay, so and the fields of Earth and the Moon are in opposite direction. And because they are in opposite direction, right, there will be a point where you cancel out. But what do you mean by cancel out there? This means that the resultant field strength is found by subtracting, like GE minus GM, subtracting both fields because they are in the opposite direction. That's why you subtract. Hence, there will be a point where it is 0. Okay, so first you explain it's a vector. If not, your subtraction will make no sense. That will be 1 mark. And the second mark is opposite direction. So that's why you get 0. Okay, continue. Determine the distance in terms of RE where your field strength is 0. So like I say, when you add them together, because opposite direction, you get minus. Okay, you get minus here, right? So now you equate them, lor. GE is equal to GM. But in order to find GE, I need the radius from the center of the Earth, in which I will label X. And if this is X and this is 60 RE, then the other side, the remaining will be 60 RE minus X. Okay, don't forget the square. Right, first order of business, cancel the G. Okay, so here people got also a funny pattern. They go and open the bracket. Why? Do you like solving quadratic equation? I would like to avoid it if I can. So I gathered all the x squares on one side of the equation. All the square put one side. All the mass put the other side. Okay, and then I substitute to find the ratio. This is a good technique to use in physics because I don't really care about the nature of the roots or number of roots or any of those things that you would care about in a pure maths paper. Okay? I would only care about... Sorry, something wrong with the computer. I will only care about if your answer is the correct SF. Okay? So different teacher will talk... Different subjects emphasizes different things. So in this case, what we care about is just the value of RE, in which after I substitute the mass of the Earth and the mass of the Moon, the ratio is 0.111, okay? So I cross multiply and find the value of X. Never ever leave an answer in a physics paper in fractions. Even if they ask you to find the ratio, just write the number, okay? Alright, so you can get 54. Alright, now you are asked to sketch the gravitational field strength. So because they are vector, and they are opposite direction, right? Definitely there will be some part of the graph that's positive and some part of the graph that's negative. And then there's another part where you will know some part will be positive and some part will be negative simply because there's a point where it's 0 ma. So if you sketch graph in maths, you will know if you are going to be 0, you are probably negative increasing to positive, that's why you pass by 0, or positive decreasing to negative, that's why you pass by 0. Okay, so first I need to decide where it's going to pass 0 or past the x-axis. I know that it will follow the ratio of 9:1, and then after that I notice you might need the working. So the total is 60 radius of the Earth, 54 is where it's 0, so what is left behind is 6. So the ratio is 9:1 or 54 to 6. So I roughly they just expect you to estimate. Unless they give you a graph grid, as long as anything that is more than 2/3 according to the mark scheme, 3/4 is better, you are fine. So this is where it is 0, this point here, okay? And we are going to think about also at the surface. At Earth is 9.81. On the surface of the Moon is not 9.81. Moon is weaker gravitational field strength. So it's around 9.81 divided by 6. So this one should be less than 1/4, so you get a shape like this. And then with a steady hand, remember the inverse square, 1 over r square. Join the curve, okay? Don't break the curve halfway like this. Okay, I try a few times. I've already edited out a lot of attempts. Ta-da! My drawing is nicer on the board, but yeah, it's okay. New skills, you guys. Anyway, 1 mark here is when your g equal to 0 at the point that is more than 3/4. Okay, and then GE and GM is positive, negative, different polarity, different positive and negative sign, and then the relative magnitude law. Earth must be much bigger, almost 6 times bigger than the Moon. All right, next question. This is also a very old question, but every year people ask me, so I decided to put it in video so people stop asking me. Okay, so in this particular video, this particular question, which is on page 31, this is page 31. Then what is that other question? Yeah, you can find one lah. Okay, so in this particular video, particular question, you have a spherical planet, okay, and then like planet Earth lah, alright? This question is kind of like a bonus in the beginning because you are asked to state the formula of the gravitational force between the planet. So just GMM over r squared. You be careful or you read the question or m is the planet, small m is the mass on the surface of the planet, and r is the distance between the surface and the center, which is what you're going to use lah. The next part will be centripetal force. So this one is moving in circle. Make sure your m looks like lowercase m, so it will be mr omega squared. Okay, next part. Normal force exerted by the planet on the mass. So step 1, I'm just going to draw a free body diagram or a force diagram of the mass near the equator. So I know that there's gravitational force that is attracted towards the center. This is the center of the planet. And then there's also normal force that's pointing away because the surface is here, so the normal must be pointing away. And this is the direction of your centripetal force. And hopefully you have not yet forgotten, centripetal force is net force. So the net force here is GMM over r squared minus n, because we take towards the center of the Earth as positive. I know it's very weird to draw normal like this, but if you look at the diagram on top, the surface is angled that way. Zoom in so you rearrange, you can find your n law, GMM over r squared minus mr omega squared. Right, next part. Explain why the normal force on the mass will have different values at the equator compared to the poles. Well, the radius of the circular orbit will decrease, right? When you go from the equator to the top part, the radius will shrink. So the value of r in the mr omega square will change, but the value of r in the GMM over r square does not change. I will draw later for you to see. So you can say that the value of r in the expression of mr omega square or in the expression of centripetal force decreases as the mass approaches the poles. Okay, and the second point would be hence the normal reaction, because if this one decrease, then the normal reaction will become smaller. Wait, my bad, it's not smaller. The normal reaction actually becomes bigger. Okay, think about this one. If your mr omega square decreases, this expression becomes smaller, right? So if this expression becomes smaller, your normal will be equal to your weight. So in other words, right, at the equator, when you stand on the weighing machine, you're actually slightly lighter. The reading is slightly smaller compared to the poles. Slightly not a lot You are not that much lighter. Don't be in denial. Okay, so the normal reaction becomes greater. I will correct this before you find them in your OneNote. Okay, next, continue. All right. So now let me draw for you. The mass is here, okay, and this r will stay the same. This is a sphere. So this r is the same because we use this value of r to find the gravitational force. Okay, but the circle actually becomes smaller, and we use this r, the radius of the rotation. So when this r decrease in the circular part, the centripetal force decrease. That's why the normal force will increase because the net force decrease. Okay, next, radius of the planet completes one revolution. Calculate the magnitude of the centripetal acceleration at the equator and one of the poles. So centripetal acceleration, if you remember the equation, AC would be r omega square. So you can place in the value 2 pi over t square, so 6.4 times 10 to the power of 6. Converted unit already, wonderful, so just substitute, don't forget the square, and you get 0.034. Alright, so that's how little it is lah. You're just going to be that little, much lighter. And on the poles, radius is 0, so there's no acceleration. Next part. In the case of a real planet, what could affect the acceleration of free fall? Radius of the planet can change along the surface, right? So your G might not be constant because you have high mountains, you have low valleys, okay? Second thing, you could say that the gravitational force could be attracted by the nearby planet. Maybe there's another moon that is too close, and the gravitational field strength of the moon will slightly impact the gravitational field strength on the surface of the planet. Number 3, the density of the planet might not be constant. And number 4, which is the example that we discussed today, the planet might be spinning. In fact, it might even be spinning on more than one axis. But the whole idea is that the planet will be spinning. Alright, so that's all for today. I will see you in the next video. Bye-bye.